So let's have a new topic in Geotechnical Engineering, and that is stress distribution in soil. Construction of a foundation causes changes in the stress, usually a net increase. The net stress increase in the soil depends on the load per unit area to which the foundation is subjected, the depth below the foundation at which the stress estimation is desired, and other factors. It is necessary to estimate the net increase of vertical stress in soil that occurs as a result of the construction of a foundation so that settlement can be calculated. This module discusses the principles of estimation of the vertical stress increase at a certain depth in soil caused by various types of loading based on the theory of elasticity. The loading type that we will consider in this lecture videos, so this video and the video to follow, are the point load, the line load, the uniformly distributed vertical strip load, the uniformly loaded circular area, and the uniformly loaded rectangular area. So these are the types of loads to which the ground is being subjected, and we will be solving for the vertical stress increase. Okay, so increase of vertical stress. Okay. So although natural soil deposits in most cases are not fully elastic, isotropic, or homogeneous materials, calculations for estimating increases in vertical stress yield fairly good results for practical work. So the computation that we will obtain from the following formulas and theories in this lecture is fairly good. Okay, so these are the stresses that we can get as the ground surface is subjected in different kinds of loading. So the first one is the stress caused by a point load. The second one is the vertical stress caused by a line load. The third one, we have two cases for the third one, because the third one is vertical stress caused by rectangularly loaded area. The first case will be when the point that we are computing for the vertical stress is below the corner of the rectangular area. So that's the first case. And the second case is this one, below the center of the rectangular area. So that's the difference. Case A is below the corner, and then case B is below the center of the rectangular area. Next, the fourth one is the vertical stress caused by a square and continuous footing. So we are going to use the pressure isobars based on Bossiness equation. So it has two cases. The square, so half of this chart will be for the square, and half part of this chart is for the continuous footing. So continuous rectangular footing. Okay. Then the fifth one, we have the approximate method for rectangular loads. So this is only approximation. If you want quick results, then we could use this. The sixth one is for vertical stress below the center of a uniformly loaded circular area. Then lastly, we have the influence chart for vertical pressure, and we will be using here the Newmark's influence chart. So in this discussions to this video and the video to follow, we will have seven formulas that we will use to compute for the vertical stress increase. Okay, so let's start with the first one. The stress caused by a point load. Okay, so look at this figure. So in this figure, the ground surface is subjected to a point load Q. So this Q here is the point load. And we are to compute for the vertical stress increase here at this point at a certain depth. So this is the ground surface. The location of this point is located at, so from point load Q with coordinate 0, 0, 0, having the axis here as downward Z, indicative of a depth, and we have here Y axis and the X axis. Okay, so the location of the point is located at point Y here, and then it's located at point X. So at point X here, and then downward Z. Okay, so that's the location of this point. Location is point at the y-axis, at a certain point the y-axis, certain point at the x-axis, and then downward at a certain depth Z. Right? So the formula to be used here is we have the Bossiness equation for the stress due to concentrated load. So we will make use of these two formulas. Okay, so these two formulas is what we are going to use. The S of Z, or we can have it as delta P, because we are computing for the stress increase. So we have here 3Q, Q being the load in Newton, times the depth Z. So let's close that up. Okay. Depth Z raised to 3 divided by 2 pi, then the radius R raised to 5. So how do we get the value of R, radius? R is equal to square root of x squared plus y squared plus z squared. So basically, that's the location of the point. Or we can use this formula here, wherein we have the load divided by the square of depth multiplied with a coefficient n sub b. Where can we get n sub b? Using this table here. Okay? This table is the values of Bossiness vertical stress coefficient n sub b. How do we use this table? Well, if we go back to the figure, we have here the big R and then the small r. The big R is when we consider all axes x, y, and z. But as for small r here, we just need the x and y. Okay? So, having the value for r, small r here, we can get the value for r divided by the depth z. Now, if we get the value for r over z here, we can get the value for n sub b. If we get the value for n sub b, then we just insert here in the equation, and we can now compute for delta p. Okay? Next, we have the number 2, vertical stress caused by a line load. Okay? So, line load. When a line load of infinite length having an intensity of Q in kilonewton per meter acts on the surface of a soil mass, the vertical stress delta P inside the soil is given by this formula. Okay? So our line load here is uniformly distributed based on this figure. So in this figure here, we have an infinite line load Q. And then what we need is to find the value of delta P at this point. So this point here is located at a depth Z, and then it is x distance from delta P. But I want you to take note that the x distance here is perpendicular from the line load. So if we look at this in the top view, if this is the line load, Q, then the location of the point here, X, should be perpendicular to the line load. Okay? So it is important to note. Or I just put that. Okay. So the formula for delta P is equal to 2 times the Q, small q, multiplied with the depth, Z raised to 3, divided by pi times the x location of the point squared plus the depth squared, and then another squared. So that's for the line load. Let's go to the third one. The third one is the vertical stress caused by a rectangularly loaded area. And we have two cases. The first case is increase in pressure below the corner of a rectangular area. So the increase in vertical stress below the corner of a rectangular area of width B and length L is given as, so this is the formula, delta P is equal to Q sub S, and then we have here the I sub Z, where we need to compute for this. M is B, B is the width. Okay, so B divided by the depth, then N is equal to L, or that is the length, divided by the depth, and then Z is depth of the point. Okay. To solve the stress at a point, divide the area into rectangles such that the point is at the corners of each rectangle. So here is an example. So given, for example, this is our this rectangle here, 4 by 6 is our foundation, and then we are asked to find the vertical stress increase at this point A. So we need to divide this rectangular foundation into 4 rectangles, making sure that each 4 rectangle has one corner into the point that we are computing. So originally we have here 6 by 4. Okay, so 6 by 4. Then we need to compute for point A here. So I need to divide this into 4 rectangles so that I will compute independently or separately for these 4 rectangles. What will happen here is that, okay, suppose that it is required to solve the increase in pressure below point A in the 4 meter by 6 meter footing shown above. The area can be divided into 4 areas, A sub 1, A sub 2, A sub 3, and A sub 4. The values of delta P in the corner of each area is then computed. The increase in pressure in the sum of delta P's of each area. Okay? And then, going back to the formula, so this is our formula for this case. Where can we find I sub z? The I sub z is located using this table here. So the table for variations of I sub z with m and n to be used. So observe that we need the value of n and the value of m. That's why we have here how we get the values of m and n. So for m, we need the width divided by the depth, and for the n, we need the length divided by the depth. Okay? So we have here the values for m and n. Amazingly, we can interchange actually n and m, because if you look at the second table here, the values for n is actually the values for m here. So we can interchange them. You can use either the table above or the table below. Okay? So that's for obtaining the value for I sub z. Let's go to the second case for the third equation. Increase in pressure below the center of rectangular area. The increase in vertical stress below the center of a rectangular area of width b and length L is given as delta P is equal to Q sub S I sub 4. Okay? So can you see now the difference of the two cases? The first case is corner of a rectangle. We are going to use the I sub z. But here, for the center of the rectangle, we are using I sub 4. Okay. So, given here the rectangular footing, we have delta P at the center of the rectangular footing at a depth z. Okay. The value of I sub 4 can be obtained using the table below. So this table is what we will use for I sub 4. Variations of I sub 4 with m sub 1 and n sub 1 to be used. So n sub 1 and m sub 1. The value of m sub 1 and n sub 1 is given by 2 times L divided by B, big B for the M sub 1, and then 2 times the Z or the depth divided by B for the N sub 1. Now how do we, or we can use this formula, L over B and Z over B, where B is the full width. This is the full width divided by 2. Okay? So we have the other formulas, the 4, 5, 6, and 7. But first, let's solve problems using those formulas number 1, 2, 3, point B. Okay, so this is the formula 3 point B. So let's apply what we have learned from these formulas, or let's apply these formulas in these examples. The first one, a concentrated load of 1,500 kilonewton is applied at the ground surface at point A, whose coordinates is 0, 0, 0. Letter A, determine the vertical stress in kilonewton at a point 2.5 meters directly below point A. Letter B, determine the vertical stress in kilonewton at a point whose coordinate is 1.5, 0, 2.5. Then C, determine the vertical stress in kilonewton at a point whose coordinate is 1.5, 2, and 2.5. So, we're looking for the delta P. Right? So, concentrated load. The type of loading here is concentrated load. So, from the 4 formulas that we have considered a while ago, we will use formula number 1. That is the formula for concentrated load. So, let's go back. So, here it is. Stress caused by a point load. So, this is the drawing. And this is the formula. So, let's use this formula. So, to use this formula to compute for delta P, so Q is given, the depth is already given, we need to find the value of R. Okay, so let's draw for the first one. So, for the first one here, we have the point load, okay, at point 0, 0. So, our point load here, Q, is equal to 1,500 kilonewton. And then, we are looking for the point 2.5 meters below, directly below the point A. So, this is point A. So, we are looking for this. So, if this is our ground surface, so we are looking for this delta P, and it is J, the depth is J 2.5 meters. So, formula here is 3QJ sub raised to 3, so delta P. All over 2 pi R raised to 5. Okay, so that's correct. But we need to find the value of R. So, the coordinate of this point here is 0, 0, 2.5. So, that's the coordinate of this point. Therefore, we have our R, square root of. So, remember that our R is this one here. X squared, Y squared, and Z squared. So, we have 0 squared Y squared plus 2.5 squared. So, R is equal to 2.5 meter. So, delta P is now equal to 3 times 1,500 times the Z of 2.5 raised to 3 divided by 2 pi 2.5 raised to 5. So, the answer now here for delta P of letter A is equal to 114.6 kilonewton. Next, letter B. So, letter B is the location of the point is here, 1.5, 0, 2.5. So, 0 here is our Y axis. If we draw, actually, if you notice, there's no need to draw, but if drawing it is required, then at least you have idea on how to draw it. So if this is our x and y axis in the ground surface, so this is our x, this is our y, and then our depth is here, depth z. Then our point load, (1,500 kilonewton). What we're looking for here is a point at what's the point again? 1.5 for the x, 0 for the y, and then 2.5 for the z. So we have here, then downward. Alright, so that's our 1.5 and then 2.5. X 1.5, z equals 2.5. This is our point for delta P. So our delta P here is 1.50, 2.5. That's the coordinate. And if we get the value for R here, that is equal to square root of 1.5 squared plus 0 for the y, then 2.5 squared for the z. So R is equal to 2.915 meter. 2.915 meters. Therefore, our delta P is now equal to, again, the formula is 3qj raised to 3 over 2 pi r raised to 5. 3 times 1,500, j is 2.5 raised to 3 over 2 pi 2.915 raised to 5. So delta P is now equal to 53.17 kilo. Okay, next we have part C. Determine the vertical stress in kilonewton at a point whose coordinate is 1.5 to 2.5. So we have the value for y now, for letter C. So again, if you have been required to draw, and this is how you go about it. X, Y, Z. This is our load. Loading is at 0.00. We have there Q15 Newton. Then the location is 1.5 for the X. So 1.5, 2 for the Y, and then you have 2.5 for the Z. So that is equal to, this is 1.5, and then downward 2.5. So 1.5 and then 2.5. So this is our delta P. And the coordinate here is 1.5 to 2.5. Okay? So we can now find the value for R. R actually is this one. It's the radius. I put here. So this is actually the R. So R is equal to square root of 1.5 squared plus 2 squared plus 2.5 squared. So R is equal to 3.5355. So delta P is now equal to 3 times 1,500 times Z of 2.5 raised to 3 over 2 pi 3.5355 raised to 5. So delta P is now equal to 20.26 kilonewton. But if we wanted to use the table, or so we have there, or we want to use the table, so this is the formula when we use the table. Q over square of that times D, NB here. Now if we want to get the value for NB, N sub B, we need the R over Z. So how do we get the value for R? So your R here, small r, you just need the values for X and Y. So that's a small r. Oops. So find the small r here, square root of the X and Y. So small r is 2.5 meters, and then r divided by Z of 2.5, so that is 2.5 divided by 2.5, that is equal to 1. From table, NB is equal to, so if our R over Z is equal to 1, so 1 here, our N sub B is 0.08440. So 0.08440. Therefore, delta P is equal to, which is Q over Z squared times NB is equal to 1,500 over 2.5 squared times 0.08440. So delta P is basically the same, 20.26 kilonewton. Okay, so this is if we use the table. Okay, so that's for number 1. Using the formula for concentrated load, or using the loadings for loadings concentrated load. Okay, let's go to number 2. We have here a line load for number 2. A line load and a point load. So it's a combination. Line load plus point load. So a line load and a point load acting on a ground surface is shown below. Determine the increase in vertical stress at point A. So this is the point A. Point A is located 2 plus 1, so 3 meters away from the line load, and it is at a depth 1.5 meters. And how about from the point load here? It's located x-axis 1.2, located 1 meters on the y-axis, and then we have here 1.5 meters for the z-axis. So I hope you're able to follow that. So let's use a different color. Can green be seen here? Okay, I'll just use blue. So this here is the x-axis. This is x. This one here is y-axis. Then downward here is the depth, and that is z. So basically, you now have your radius r, big R. Now how about the formula for line load? So the formula for line load. So line load is formula number 2. Vertical stress caused by a line load. So here is our formula for the line load. Delta P is equal to 2 times small q z, or the depth, raised to 3 divided by pi, the x distance squared plus the depth z squared, then all of them squared. Then always remember, you need the x distance perpendicular to the point of delta P. Okay, so as you can see from the figure, yes, the x distance here, for the line load, this is the x distance, and it is perpendicular to the point. So for the line load, okay, so I think we got the point now there. So delta P is equal to the delta P of the line load plus the delta P of the point load, or the concentrated load. So the formula for delta P for the line load is 2 small q depth raised to 3 all over, so that is all over pi x distance squared plus z squared, all of them squared, plus the point load here is 3q z raised to 3 all over 2 pi r raised to 5. Now for the line load, so for the line load, we have our x here is 2 plus 1 is equal to 3 meters. Z is 1.5 meters. For the point load, we need the big Q here is 600. So small q here is 150 kilonewton per meter. Big Q is 650 kilonewton. And then we have here the R, square root of the X, 1.2 plus square 1.2 squared, then 1 squared plus 1.5 squared R is equal to 2.1656 meters. Okay, going back now to the formula. You have 2 times 150 times Z, the depth is 1.5 raised to 3 all over pi. Then the distance 3 meters squared plus 1.5 squared plus 3 times 650, the depth of 1.5 raised to 3 all over 2 pi times the radius 2.1656 raised to 5. So delta P is now equal to 24.537 kilopascal. So that's for number 2. Let's go to number 3. A rectangular concrete slab 3 meters by 4.5 meters is shown below. It rests on the surface of a soil mass. So, as you can see here from this figure, so this is the plan. So this is the plan of the slab. Okay, rectangular concrete slab. Then this is the soil profile along with the cross-section of the concrete slab. So this shows the length, and then this shows the width of the slab. Then in the soil profile, we have the depth of the point A, so point A and point B. And we have also the depth of the point C. And the location of point C is 2.7 meters from the center of the concrete slab. And the location of point B is just at the corner of the, or the side of the concrete slab. Right? So using this plan and profile, okay, we have here the load on the slab is 1620 kilonewton. So this is a point load, 1620 kilonewton. But this 1620 is on the slab and not on the soil. So what will happen here is that 1620 kilonewton, if we transfer that onto the slab, what will happen? It will be distributed on the slab, so rectangularly distributed load. So it becomes this case number 3, or the formula number 3, rectangularly loaded area. Okay. So the point load is transferred into the concrete slab, the rectangular concrete slab, and it becomes a rectangularly loaded area. So we need to find, so there's A to H here. First, we need to determine the soil stress below the slab. B, determine the vertical stress increase at point A using delta P Q sub S I Z. The question, what's this? That's the formula for case A under number 3. So case A, or 3-A, is wherein the point is located below the corner of a rectangular area. Okay, so that's for letter B. Letter C, determine the vertical stress increase at point A using this formula here, delta P Q sub S, then I sub 4. And I sub 4 is case 3-B, wherein the point is below the center of a rectangular area. Okay. Then we have here letter E or letter D. Letter D is determine the vertical stress increase at point B, this time point B, using delta P QS I sub Z. Same with B here. So we are going to use 3-A formula. Okay. Next, letter E, determine the vertical stress increase at points A and B using the approximate method, which we will discuss in the next videos. So, meaning, we will solve for A to D. Okay, so A to D for this video. The next ones, so E, F, G, and H will be in part 2 of this video. So we have here the part 1, then this is for the part 2. Okay, so let's solve for A, B, C, and D. First one is letter A. Determine the soil stress below the slab. So take note, it's looking for soil stress. What's the unit for stress again? That is in kilopascal. What's given in the problem? We have 1620 kilonewton, which is a point load. So how do you get kilopascal? So what we're looking here is the stress of the soil, small q. And that is, we have there the force over the area. So we have there 1620 kilonewton divided by the area of this slab, which is 3 times 4.5. So that becomes kilonewton per meter squared. So we have 120 kilo. So that's for letter A. Now we're done for letter A. Let's go to letter B. So again, for letter B, we have there the case 3-A. How to solve again for case 3-A? We need to, says there, divide the area into rectangles such that the point is at the corners of each rectangle. So we will take this into here. So this is letter B. So we have here point A. We are solving for point A only. So meaning we are not going to concentrate on point B. So let's remove point B here. So let's concentrate on point A. Divide it into 4 rectangles. What can you notice when we divided it into 4 rectangles? Remember that point A is at the center of the rectangle, the rectangular concrete slab. Therefore, our A1, A2, A3, A4. So we can therefore conclude that A1 is equal to A2 is equal to A3 is equal to A4. Okay, so they are all equal areas. So what's the formula that we are going to use again? We're going to use delta P is equal to QS. Our QS here is what we have solved a while ago. So this is Q, soil stress, or Q, still the same, Q sub S. Q sub S IJ, and then we will multiply that into 4 because delta P1 is equal to delta P2 is equal to delta P3 is equal to delta P4. So we'll just basically divide the answer here into 4. Multiply. I should say multiply into 4. So we have QS. What we need is I sub Z. If we are looking for I sub Z, we are going to use this table here. And we need the values for M and N. To get the values for M and N, we have the formula here. B divided by Z, N is equal to L divided by Z. Okay, so we need to find B. Our B is 3 meters. L is 4.5 meters. Therefore, M is equal to B over Z. So that is equal to 3 divided by, what's our Z again? Z is here. That is Z, 3 meters. Right? So we have there Z equals 3 meters. 3, therefore M is equal to 1. N is equal to L over Z. And we have here 4.5 divided by 3. So, oh yeah, I forgot. We divided it into, so this is wrong. I think it's best if we just draw it. So I want you to see where I went wrong. So this here, we took a sub 1 for example. What is 4.5 divided by 2? That is equal to 2.25. Then 3 divided by 2 is 1.5. Okay. Therefore, our B here is equal to 1.5. Our L is equal to 2.25. And our Z is equal to 3 meters. Therefore, M is equal to B over Z is equal to 1.5 divided by, our Z is 3. So that is equal to 0.5 meter. Why did I? N is equal to L over Z equals 2.25 divided by 3. That is 0.75 meter. Okay, so let's go to the table here. So remember, we have the value for M is equal to 0.5. Then we have N equals 0.75. So the table, let's go to the table for I sub Z. Take note, this is the table for I sub Z. Our M a while ago is 0.5. So 0.5 for M. So there you go, our 0.5. Next, for the N, we have 0.75. So N here is, there's no 0.75. We have here, all we have here is 0.70 and 0.80. So we have here the value for IZ. In between 0.1034 and 0.1103. Okay? So, if you look at this closely, it's easy because you just have to divide it into 2. Because 0.75 is located in between 0.70 and 0.80. So, you have there I sub j is equal to 0.1034 plus 0.1103 divided by 2. But what if, okay, so maybe I should remove this because you might have the impression that you just have to divide it into 2. Because what if it's not exactly 0.75? What if you got here a value, for example, 0.72? So you cannot just simply divide this 2 here into 2. So, how will we get the value of 0.72? So, this table actually uses linear scale. So, we can interpolate this linearly. So, we will use linear interpolation. So, how to make this clearer from table. So from the table, we got here, so for m is equal to 0.5, n is equal to 0.7, ij is equal to 0.1034, and then for m is equal to 0.5, the n is equal to 0.8, ij is equal to 0.1103. So using linear interpolation, so let's just put it here aside. Using linear interpolation, we can obtain 0.75. Okay, in your calculator, for faster. So what we did before is we use the logarithmic scale. This time, let's use the linear scale. So go to mode, choose there 3 stat. So mode 3 stat, and then you have there number 2, the linear 1, so a plus bx. Number 2, choose number 2. Then you will have there the table. So we have here x, and we have here the y. Frequency for x, let's put here the 0.7. We're missing the 0.75, right? 0.8. So this is what we're missing, 0.75. 0.7, we have 0.1034, then we have 0.1103. Okay, so don't put here, don't put this one. I just write here so that we are just aware of what we're looking for. Okay, so input 0.7 equals 0.8 equals, then go to the left here, right, I should say, go to the right, then input 0.1034 equals 0.1103 equals, then click AC, I'm using Casio FX115ES. So AC, we have here shift, click shift, then 1. Shift 1, we have there start. Then click there 7, which is reg. Then use, so what we're missing here, take note, what we're missing is y. So choose y hat 5, so choose y hat there. And then input here the x value of x 0.75, then y hat is equal to 0.10685. So you now have the value of, so therefore n, okay, so therefore we have m is equal to 0.5, n is equal to 0.75, we have there the ij equals 0.10685. Then we can now compute for this, which we have been transferring over and over. So 120, so to return, you just have to mode and then computer. So 120 and then 0.10685. Then you multiply it with 4. Again, why 4? Because we did all these calculations here by just using a sub 1. And remember, we divided into 4 rectangles, all of which are equal. So the value of delta P here will be multiplied with 4. So 120 times 0.10685 times 4 is now equal to 51.288 kilopascal. Right? So we now have our B. Next, question C. Determine the vertical stress increase at point A using the delta P is equal to QS I sub 4. So he wants us to use this 3-B case. Right? So what's this case again? If we put the point at the center of a rectangular area. Okay, let's see the difference between the two, the 3-A and 3-B. So this is letter C. Then let's remove here B. We're not computing for B. Now you have to take attention here. Our point A is already at the center of the rectangular concrete slab. So our formula here to be used is delta P equals Q sub S and then I sub 4. We already know what's Q sub S, that is 120. How do we get I sub 4? To compute for I sub 4 here, we need this table. So table for I sub 4, and we will use here the M sub 1 and N sub 1. Computing for M sub 1, we have there twice of L, the length, divided by the B. And then we have N sub 1 is twice of the depth divided by B. Okay? So here, our B is 3 meters. So B is 3 meters, L is 4.5 meters, Z is, again, what's the Z? The Z here is 3 meters. Therefore, we have M sub 1, 2L over B. 2L over B is equal to twice of 4.5 divided by 3. So M1 is equal to 3. So M sub 1 is equal to 3, then N sub 1 is twice of depth over B. So twice of 3 over 3. So N now is equal to 2. So from the, okay, so M sub 1 is 3, N sub 1 is 2. From the table, M sub 1 is 3, N sub 1 is 2. So this goes to here. 0.5254. Therefore, so from table, I sub 4 is 0.5254. So multiply it with 120. So delta P is now equal to 63.048 kilopascal. So that's for letter C. Let's go to letter D, the last one for this video. And then the rest, we will solve them in the part 2 of this video, this topic. Letter D. Determine the vertical stress increase at point B using delta P equals QS I sub Z. Now, what's I sub Z again? That is the corner of the rectangular area, I sub Z. So, let's concentrate on letter D. So, let's put another one here. Okay. There you go. That's for letter D. Now this time, what we are looking for is B, not A. So we're done with A. So how do you divide this rectangle so that the point we're looking for, this point B, is at the corner of each rectangle? We will divide it into two rectangles. So that's the first one, A sub 1. Then the second one, let's use a different color. Then this is A sub 2. Okay. Darker green. So A sub 2. Now for the so what will happen since we divide it into 2? So let's use A sub 1 here, which have the dimension of 4.5 divided by 2 is 2.25. Then we have here 3 meters. So this becomes your base, this becomes your L because it's longer. Now, what can we conclude? Again, A1 is equal to A2, the same area. Therefore, delta P1 is equal to delta P2. So, our answer later on for delta P will be multiplied by 2. Okay? Next, we need so the formula is delta P Q sub S I sub Z. Compute for the values of M and N. So having B is 2.25, L is 3 meters, and then Z is equal to 3 meters. Is point B 3 meters below? Yes. So this is point B, and its depth is the same as point A, which is 3 meters. Right? So let's find now the value for M. Again, a while ago, how do we compute for M? That is B divided by the depth, and then N is B over Z, N is B over Z. So, L, should say L. So our B here is 2.25 divided by 3. That is equal to 0.75 again. And then we have L3. 3 over 3 divided. So that is 1. From the table, so from this table, we have M is 0.75. So in between here, between 0.7 and 0.8. Then we have N is equal to 1. So N is here. Therefore, we need this. So again, dm is 0.75. So it's very obvious that you can get the value for I sub z. You just divide 0.4091. You just divide the sum of 0.4091 and 0.1598. Divide it into 2. But then again, what if we don't get 0.75, rather it's 0.72? Again, we will use linear interpolation, just as we did here a while ago, using linear interpolation. So using calculator. So we need to look for using linear interpolation. So what did we get here from the table? So let's write here first before we proceed here. From table, for m is equal to 0.7, n is equal to 1, I sub z is equal to 0.1491. For m is equal to 0.8, n is equal to 1, I sub z is equal to 0.1598. So using linear interpolation, x and y here, okay, so we have here 0.7, 0.1491, we're looking for 0.75, missing 0.8, so 0.1598. Okay, therefore I think we have it here in our calculator. Stat, we are using here a plus bx. So we have the frequency 0.7 equals 0.8 equals, then go to y. We have there 0.1491 equals 0.1598 equals. Then we clear shift stat, and then where is the inputting data? So the statistics. Okay, I think we cannot use this one here. Oops. So I'm not used to this one yet. Just use our calculator. What you will get there is, so use y hat again. So 0.75 y hat, and that is equal to 0.15445. Okay, so we were able to find Ij is equal to 0.15445. Substitute here, so 120 times 0.15445. So delta P is now equal to 37.068 kilopascal. Right? So that's for letter D. So I really want to use this. So mode in the next video. Right, so that's for this video. For the part 2 of our video, so we will use the other formulas. So in this video, we just discuss formulas for case 1, 2, 3-B. The line load, the point load, then the rectangular loaded area. So the next video we will have the Bossiness equation, the pressure isobars, and approximate method, the circular area, uniformly loaded circular area, and the influence chart using Newmark's influence chart. Okay, so that's it for this video.